I'm Ray.
And I'm Brian.
Hey, and this is Two Skis Walk Into a R. We're going to do an ANOVA workflow, and not to give anything away, but this one might need a transformation. So this might equip you to do transformations.
We're going to go through the workflow not knowing that it might need a transformation.
But hey, listen. We did another video on the ANOVA workflow where we analyzed the... Ooh, that's not what I wanted to show. That's giving too much away right there. That was where we analyzed the sepal width of these iris flowers. This time we're going to do petal width of these flowers. And so if you have not watched the video on sepal width, you have to stop this video right now and go watch the one on sepal width. The ANOVA workflow. No transformation needed.
Because we're going to make some assumptions and just kind of move right on.
Yeah, we're going to kind of, So if you've not seen that and you're at all confused, you're going to be, this will make you extra confused. But if you're down with that previous video, you're going to be good. Okay, so here we are back at the same script. And I've saved it, ANOVA iris.r.
The same script from the previous
video. From the previous video, right, exactly. And so we brought in our iris data frame here and checked it out. And then I did this whole analysis of the sepal width versus species. So I'm going to go ahead and I'm going to copy this whole thing.
Well-organized script that we did in the past,
exactly.
And we saved it in a place that we can find it later.
Right. So edit, copy, and now I'm going to go to the end here, and now I'm going to paste that exact same thing. This is copy, paste, adjust, folks. Copy, paste, adjust. So now I'm going to go up here. This is not going to be sepal. This is going to be petal width versus species. And I'm going to change the mean petal width. The mean petal width. I don't know. And then here, instead of sepal width, we're going to change that to petal width. And I'm going to just copy that so I can easily paste. Let's see. This doesn't.
It's good amount of caffeine in you and being very conscientious line by line. Because if you miss something, it won't work.
Right. The fact that I'm just going to overwrite my statistical object with M is going to make all of this behave very nicely. Mm-hmm. Okay, so let's look at our raw. So now we have our null and alternative hypotheses. Let's look at our raw data. Whoa!
You look pretty different, Ray.
Yeah, man. I think your odds of getting data like this, assuming that in fact the populations are the same, is so small. So I think we're going to get some statistical significance here. And I just ran the object. So now we have our object in there, and now I'm going to get the output from that. And oh my gosh, yes, your odds of getting data like this, assuming there's no difference, is as close to zero as R can possibly give us. Okay, and we do a post hoc. They're all going to be so different, you can't believe it. But now we get to the real question. So we got, we did our visualization, we made our statistical object, we got our output, we did our post hoc. But now, is the p-value valid? We have to verify that the assumptions are met.
This is an essential and key part of the statistical analysis. Can we actually trust the p-value that was always going to be given to us?
Yes, exactly.
Whether we met the assumptions or not.
Precisely. So here we go. Here's the histogram. It's normal-ish.
Normal-ish.
QQ norm and QQ line. That's pretty normal-ish. They're falling on the line. And then Shapiro. Okay, Shapiro passes. Remember, our Shapiro is, we draw that line at 0.001, and we're bigger than that, so we're going to conclude that the data were drawn from a normal distribution. So far, so good. You're like, why am I watching this video about transformations? But now let's check out the result. Whoa, look at that. That looks heteroscedastic to me. That does not look homoscedastic. The variance looks unequal.
The variance looks unequal. Yeah. So heteroscedastic, variance unequal. Yep. Homoscedastic, which this is not, variance or the spread looks equal.
Right. So Bartlett test
will give us a statistical approach to that.
So it's super small. And the Bartlett's test, the null is that the variance is equal among groups, that is homoscedastic, and we're way smaller than 0.01, so we have to go with the alternative.
So I would consider that a rejecting of the null hypothesis, variance is equal, and accepting the alternative for the Bartlett, which is variance is not equal.
Okay, yeah, and you could tell how delicate Brian was being with his language there. I'm forever baffled by all that talk of accepting or believing or not believing or rejecting or not rejecting. Anyway, we all agree.
We all agree.
We all agree. We're going to have to make a transformation. So this is a really helpful. So the p-value is not valid. So we have to go here, and we have to do one of these transformations. And, log's a nice one. Let's try a log. Did you try log? Let's try log.
We can try a log.
Let's try log. So you put that right in where you create the statistical object. It goes right there in the response.
So no need to rewrite that line out. You can go back up and edit that one line of code to do a log transformation.
Boom. So I just put it right there, and now that transformation is going to exist. Once I run this, it's going to live inside of my statistical object, which I'm overwriting, which is beautiful because then now I can get all of this other stuff.
Without retyping
anything.
The whole script.
Yeah, isn't that nice? And we still have to verify that the residuals are normal. Ooh, this is actually looking a little worse, Brian.
It looks a little worse to me, too.
Oh, now we don't even pass.
How can you tell it's worse? Because it's not really fitting on all of those data residuals on the line.
Hideous. And this p-value for the Shapiro-Wilk test is super tiny. And yeah, so
it's a red flag fail there.
Yeah, red flag fail. So let's try something different, maybe a reciprocal, 1 over the response. We'll try that. So I'm going to go right back up here, and we'll do 1 divided by all that stuff. We can run that, and then we'll check our histogram. Garbage.
Like garbage. Not going to work.
Not going to work. Super terrible. Awful. What's your favorite transformation?
Well, in this particular case, I always try the log first.
Yeah.
And then the second one I try as a workflow, square root always tends to be a really potentially helpful transformation.
Let's try it. So there's 2 ways to do this. You could type sqrt, and that's the square root function. I prefer to raise this whole thing to the 0.5 power. So raise it with that little caret.
Raise?
Yes, raise, 0.5. That's the square root. And then the nice thing about that is if this doesn't work, you can then easily change that to like a quarter root transformation or a 3/4 root transformation or something like that. So let's try this square root. All right.
Grade
so I ran
school math
it.
Back to haunt you.
Boom. I wasn't learning that in grade school.
Oh no. Maybe I went to the wrong or right school.
I think the right school. So normal. The data are again looking normal enough for us. We're happy about that because that's greater than 0.001. And so now this is what we really care about. Ooh, okay. It's still not perfectly homoscedastic, but this is looking
pretty
better.
good.
It's looking a lot better than it used to look. And so the Bartlett test, Bartlett is totally happy. This is much larger than 0.01. And so we would conclude that we'll accept the null that the data were drawn from homoscedastic distribution. Okay, so the variances are equal enough, which means our p-value is valid. Now since we did this transformation, actually, we should probably double check our p-value. It might have changed, but probably not. Oh, and let's go back to our raw data graph. Anytime I'm looking at the actual output of the ANOVA, I really want to look at the raw data
So
graph.
just like in the first video, could we give it a Control-L?
Yeah.
Or Command-L, clear out and sweep out and start from the beginning so we can not get confused with all of our piles of graphs that we collect.
Yeah. So you know how on a PC, usually you're doing Control whatever, and on a Mac, you're doing Command whatever? Strange thing. On this one particular instance, if you want to clear out the console, it's Control-L on a PC and a Mac. Super surprising.
Sometimes we all come together.
I know. Okay. So we're going to clear all this stuff out, and then we will start from the top, load our data back in there. I'm going to skip down to our second ANOVA.
That's great.
I really probably should have given these guys some equals so they could actually become
their own categories.
Their own sections.
Yep, their own sections are pretty nice.
Yep. Let's do that. Boom, 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 boom. And now I tried to navigate there. I don't know if you noticed me.
Yep, absolutely.
So anyway, there's our raw data. There's our ANOVA with the transformation in there.
Mm-hmm.
And now we'll get the output. It's still hugely statistically significant. Your odds of getting data like this, assuming that the means are actually the same at the population level, is astronomically small. And again, I bet the Tukey's are going to say the same thing. All three of these species have statistically significant differences. It's hard to say all those S's. Well, we were doing some toy boat a minute ago, right?
toy boat.
Yeah,
I see. The tongue twisters are. Good luck out there, team.
Good luck out there, team. All right, so they're still normal and they're still homoscedastic. So there you have it. And we could just make a note, right? You would, if square root hadn't worked, I might try quarter root, 3/4 root. I might even square it. Mm-hmm. If those didn't work, and it really mattered, I'd go talk to a statistician.
Absolutely.
If you're like, you just need, it's time to get this done, then no transformation is successful, then you're going to use a non-parametric test, which in the case of ANOVA is a Kruskal-Wallis test.
Mm-hmm.
Right. Okay. That sounds good to me.